Okay, so I'm going to have a little video, talk about some things I hope that you learned. This was one screen from what you guys did with your teammates. You had the challenge to change the mean and the median, but I just want to use this slide to talk about how the mean and the median will change depending on the data. So both of these, or the blue one, is relatively normal set of data. It's relatively uniform. Okay, it doesn't look perfectly uniform like some of your examples, but because the mean and the median are equal, you can say that that is a uniform distribution. The bottom one is slightly skewed. Which direction is it skewed? If the median is less than the mean. So the middle number is lower than the mean. So you can see this data is skewed to the right, and that would make the average higher. So the skewness always changes the mean. So we're going to move these a little bit. We're going to watch what happens. If I move this last dot over to the right, skew it even further, that should mean that my median should stay 3, but my mean should do what? Now let me go higher than 10. The mean, as I skew this further, is going up. So as I skew it to the right, the mean is higher than the median. When you were asked to change it so that it changed, I'm going to skew this to the other direction. So it won't let you go beyond 0, I guess. So if I want to skew it to the left, I'm going to have to move these ones over down here. Say I want a data set that's skewed left, means the tail is going off to the left, then I would expect my mean to drop below my median. I would expect my mean to drop below my median as I start to skew it. Oh, my mean definitely dropped below the median. I'm not sure when that happened, but it definitely happened somewhere down the road. As I was moving these and I was skewing it left, now my median is higher than my mean. Okay, so skewness can always be determined, if it's left or right skewed, by the mean and the median. If the mean is lower than the median, that means it's skewed left. If they're the same, it's normal or uniform, and if it's skewed right, then the mean is higher than the median. Okay, next topic. That's what I hope that you learned with your partner. That was the main thing I wanted you to learn, was as you move those dots, as you moved data points, as data points moved from skewing left to right, what happened to the mean and the median? So with that idea, is this skewed right or left? So let's look down at the data. Is it skewed right or left? Okay, if I change this last data point, this 23, the one that's way out here, kind of way out away from the rest of the data, if I change that to a much higher number, what will happen to the mean and the median? Is that what you expected? If I change it to a much lower number, okay, I'm hoping that's what we learned. I'm hoping that that was a good review of what you talked about with your partner. The things we did not talk about with Desmos, one more thing that it has is it has the ability to make a histogram. So a histogram we didn't talk about. So here I have just a simple set of data, 10 elements, and I've made a dot plot. If I want to make a histogram, come over here to distribution and make a histogram. And oops, I put it in the wrong place. Let's put it down below. I want to make a histogram, and I want it to be of the same data set L. You can see how that goes directly on top of those dots. There's just the idea of what Desmos does in histogram. Desmos does not, however, categorize the data as far as what these things represented. Only will do a histogram for numbers. Maybe in the future someday they'll have some other way to do it, but for now it's numbers. So if you want to use this when I ask you to make a histogram, you are welcome to do that, but it's going to take something a little specific, and we're going to talk about that. So one more thing that Desmos can do that we haven't done is we talk about a linear regression, or a finding a line of best fit is really what we're looking for. In 8th grade, you might have plotted some points like this, or 7th grade, and you might have even put something down. Some teachers will have you put a line of spaghetti or something straight like that, right? Or else they just have you move your ruler until you feel like you've got a pretty good line of best fit, and then you decide what the slope and the intercept will be based on that line. I like using spaghetti. I like if we were in person, us doing that and being able to oh, I see what's going on here. Being able to get a feel for what we're really talking about, but we're not in the classroom, so we are going to show you how to do this. So here are data points. Here's a table that with all of those data points in it. I can make a line of best fit by looking under my function, under stats. Where is it? It is under, oh, it's not under anything. Oh my goodness, I can't believe I forgot this. All I'm going to type in is what my y's and my x's are called. In this case, y1 is my y. It's approximately equal to is what we're going to use. It's approximate sign, not the equal sign, but approximate sign. It's approximately equal to mx1. X1 is the other coordinate pair that I have, plus b. Sorry about that. Brain lapse for a minute. This is going to give us our line of best fit. So our line, here's our m, and here's our b. So our line of best fit, and Desmos is super cool, right? So we can move this and we can see what happens, right? So if I move one of these dots around, as I move the dots around, how does moving each dot affect the line of best fit, right? How does it do that? If they're all kind of close together, sort of, and then you have this one little row guy way down here, it does affect it in that they're all lower than they would be. So this is kind of a fun thing to play with. I probably should have put this in there for you guys to play with, but I'll give it to you later, and you guys can play around with this. You can even look it up. It's statistics, linear regression under Desmos. It's one of their graphs. If you go, if you're in Desmos and you hit this little thing, one of the graphs, if you search and you search linear regression, it'll come up. Okay, so if you want to check that out, feel free to check that out. Now, what that is, if this is my slope and my y-intercept, if I were to graph the graph of y equals, my m is 0.517949 is what they rounded it as close as possible to, x plus, and it says that my interception is 2 point, am I getting closer? I'm getting close. Is it going to be right on top of the other line? It's going to be extremely close. So you would know that this m and this b really are the slope and the intercept of the line of best fit. Okay, so if you want to use this linear regression in your Desmos, you will, or in your stat project, you're just going to type in y1 or whatever your value is approximately equal to mx, whatever your other value, x value is, plus b. I'm going to do this again for you as an example in just a minute when I'm comparing some of our census data. Which brings me to our next topic, census data. So here's your wonderful census data. Here's all of those things that you guys notice there is no personal information. I hope that you know that. There's no personal information that was gathered from you other than who you are, the gender, the age, the hand, your height in centimeters, your foot length in centimeters, all of the things that you put in, but there's no personal information. There's no way for you to be able to be contacted or traced according to this. Just want to be really clear on that. Now, I'm going to demonstrate how to use this data to come up with a couple different comparisons and how you might use some data. One thing I'm going to talk about is the time that it takes you to get to school. How much time does it take you to get to school? So it takes you, so I don't have anything in here. I'm going to show you what I might do. So the time to get to school was right here, time to get to school. And I would actually, what I would do is I would take that information, I would just copy it. Now, you don't have to do this first step that I'm going to do, but you're probably going to want to when you see what happens. So I'm going to copy this with my Control C. I'm going to go where it says time, and I'm going to enter it in there, which I already did. And it should just come up just like this. Now, couple things to notice. There's only 82 people that responded, which makes me really sad because there's 104 algebra students. And that was the only thing I gave you to do on Friday. So I don't understand why you didn't do this at all. Also, you can see that what I want you to try, I was going to have you try this. So how you'll do this, so I'm going to copy this data, just like we had it. I'm going to go into a Desmos tab, check this out, and all I have to do is paste it right there. Actually, no. See, that didn't work because I got 82 and nothing is in a list or any way that I can make a stat function out of it. Okay, there's an error sign at the top. It doesn't seem to make sense. Okay, so I'm just going to delete that. I'm going to show you what the problem is. So the problem is that people decided not to do what they ask. They put some units in there, right? So that person put units. And then as I go down, here's someone who put approximately 25. Well, a computer doesn't do that. Computer doesn't understand that. And this is real data, right? Like this is what a real statistician would have to do. They would have to go in and change data. They would have to go in and see what's going on. Someone here put May 10th. Do you think that's really May 10th? Nope. I think they probably meant 5 to 10 minutes. So let's say let's put an average of 7.5 minutes, okay? I think that's probably what they meant. When I go here, I'm going to get rid of the minutes. So this is, like I said, it's real life data. This is what you'd have to do when you're using data. A lot of the times you guys see in school, things that are already pretty and nice. So I'm going to take this. Now I'm going to copy this. Here's the cool part. I'm going to go over here to time to school. I hope it works. And I'm going to paste it. And look at that. It went right into a list for me. It went right into a list. So I am going to list. I'm going to name that list. So I'm going to go back to the beginning and I'm going to name it. What are we going to name it? T for time. How about T for time? Probably a much faster way to do this. Capital T equals time. So one thing I want you to be able to do is to make a, find the stats for this, right? So find the mean of the time that it takes. And I want you to be able to find the median of the time that it takes the average kid to get to school. They are pretty close. The mean is 15.7 and the median is 15. That is a pretty good distribution. I would say that is really not skewed. If anything, it's skewed a little bit. Which direction would it be skewed? Take a look at our box plot and see if that'll help us. So box plot of T doesn't look very skewed. It's got an outlier out here. Ooh, it actually got rid of our outliers because check it out. It tells you, do you want to exclude the outliers? If I don't exclude the outlier, if I leave that in there, it goes a little further. So because our mean is just a little bit higher than our median, you should have guessed that it was going to be a little skewed to the right, especially if you include the outliers. It's even still skewed if you include if you exclude them, but let's leave them included. I also want you to be able to make a dot plot, and I want you to think about what that means. Let's change the color. That's not that pretty of a color. And what else can we change? We can change, if we hold that down, we can change it to be, let's do it just a different color here. And then let's move this so we can see it a little better. Oh man, that histogram is right on top of it, right? So it's a little bit weird. Let's go back to my my box plot, or my, like I said, histogram, sorry guys, box plot, and let's make it at about 17, so it'll just raise up a little bit. So I offset it 17 so I can see it above it. Now I can see how this lines up, and I can see that my median is right where all those dots are. That makes a whole lot of sense to me. Does it make sense to you? Does it look like about 25% of the data is where the first box is, and 25% of the data is here? So other things that you should be able to do is you should be able to find the IQR. In order to find the IQR, I am going to put in 2 quartiles. I'm going to use my T, but I want to know quartile 3 is 20. I also want to know, the other thing that I've learned to do is the quartile 1. Okay, then I know, and I can insert a little note here. So I'm going to insert a note. I can say that 20 minus 9 is 11. The IQR is 11. We should be able to figure out what the IQR is. The other way that we would compare 2 different data sets would be to use a standard deviation. You can also find the standard deviation of T, which is 8.447. We're not comparing the IQR to the standard deviation. Those 2 things are like comparing apples and oranges. We would be comparing the IQR to another set of data, and we would be comparing the standard deviation to another set of data. So when you do your statistics project, what you might do is go to the census data set, or I can give it to you if you're leery of that, a set of all of the US people, or we can take 50 random people from the or 81 random people, and you can compare the United States data to our data at Bell, to our 81 people at Bell that took the survey. So that's one way that you can use this US Census data. Okay, so I do expect you to be able to compare 2 sets of data using these one data statistics, using the interquartile range, using standard deviation, even the range, and the mean and the median. Okay, and determining what kind of data it is. Since our mean and median are fairly close, it's a fairly close, fairly uniform, slightly skewed to the right, right? Because it's a little bit higher. So it is you would say this is slightly skewed to the right, this data. Okay, go back. I am going to look at my original data. One more thing I was going to show is way to get to school. So when I go to here to school, I would copy that, and I've already done that to save time on this, and I put it in column A. So there's 2 ways that you can show a histogram. You're in Google Sheets. It's super easy to do this in Google Sheets. If you want to use Google Sheets, you are welcome to. You can also use Desmos. I'm going to show you both ways relatively quickly. Google Sheets. I'm going to highlight what I want to use. So I've highlighted column A, and I'm going to insert a chart. And the chart that I'm going to insert is not a pie chart, but I'm going to come over here and I'm going to say I want a bar chart. That simple. Nearly 50 people were in a car. Then about little less than 30 took the bus, and a very few people rode skateboards or walked. Super easy, so easy when you're in Sheets to make a histogram. You're welcome to use this. You would need to download this, like with an image, and then put that image into the project that you're going to be doing, right? So you're welcome to do it, to use this as a method. The other way that you can do this is you can, if you want to do it all in Desmos, is you could copy this information. So I'm going to copy this. I'm going to control copy it. And I'm going to show you what I did. And I did ways to get to school. I am going to, again, put my, I'm going to put, let's go ahead and put W equals, and I'm going to put my data set in there. There are 81 elements, and I named it W. And you can see it's made a histogram here in Desmos. And you could change the, you could, mess with your settings so that it's a little wider if you wanted to make this pretty. And then you could insert it that way. So notice that I did put notes, so you can insert a note. I inserted these notes. It said, let 1 be car, let 2 be bus, let 3 be skateboard, and 4 be walk. Because you just don't, you have to say what each thing is if you're using Desmos, because Desmos is only going to graph numbers, not words. Okay. So, but you can also see that it's exactly the same information as it was when we were in our, Excel sheet, not Excel, sheets, when we were in our sheets. This is Google Sheets. Okay. Now, last thing I want to show you is that same thing where we talked about the linear regression. So I want to take 2 bits of information. So I wanted to do arm's length, and I wanted to do versus foot length. I was wondering if foot length and arm span were related in some way, and what would the relation be? So I would have taken this information, but take a look, gather down here. Notice that even though you were asked to put it into centimeters, somebody said 8.5 inches, I think, and they said 56.8 inches. And then the ones that were actually, so they didn't read the units or didn't read what they want to do, or they just, didn't do it. So like here's someone who just didn't do it. They just chose not to do it. Why bother getting up to get a ruler, right? Or this person, I don't know. Well, nobody knows. Nobody actually knows that stuff. We don't know how big our foot is in centimeters until or how high we are in centimeters until we measure. So, or if you knew how many feet, I'm pretty sure you could do the conversions. You guys are in algebra. You're amazing. You could have done that. So you can see there's a lot of holes. Okay. So again, real data, real people. This is what a statistician would have to do. So this is what I did. I went in and I just cleaned up the data, right? Now, things that were missing, I just put zeros so you guys can see what effect that has. And I'm going to ask you to either put zeros or exclude those data points, but I'm going to ask you to explain what you did and why you chose what you chose. And I'm going to ask you to talk about the difficulties in real data, like what happened, what did you see? So for instance, we saw that some people used feet instead of centimeters. So you're going to talk about those kinds of things in your project, right? What happened? So to use Desmos, it's super easy. You do not have to copy all these down. Just a year ago, you had to copy all these down. They are improving all the time. So I'm going to copy this with my control copy. I'm going to go to my arm's length that I've already labeled. I'm going to go to the first thing. I'm just going to put it in and check it out. It went into a table for me. It's so amazing. So that's super cool, right? And then we talked about how we do linear regression. How do we do a line of best fit? Now, interestingly enough, look at that data. Do you think that these weird data points down here where zeros are, is anybody's arm span 0? Is anybody's foot size 0? So you're going to talk about, when you do this, how real people, for whatever reason, just didn't do it correctly, didn't read the directions, didn't care enough to find a ruler, will change your data set, right? And so then you will be evaluating how good is your data. So remember we said what are these called? Let me see what they called them. X1 and Y1. So Y1 equals mx1 plus b. Oh, not equals. That's silly. Almost equals, right? Almost equals. What does it almost equal? It almost equals this, where our slope is 5.5 and our y-intercept is 11.63. Now, most of the data you can see is way above that. So I'm thinking our line of best fit really did get pulled down quite a bit by these odd data points, these outliers, but that's okay because that's real data. So we talk about. So again, double check yourself. Make sure that if I were to put in the function y equals 5.55571 x plus, am I going to get right on it? Am I going to get right there? Plus 11.0633? Yep, we're right on it. So that is in fact your line of best fit. So if you were going to, if you had someone out here that had 35, there you go. If you had 35, you could guess if their feet were 35 centimeters, if their data was like ours, if their feet was 35 centimeters, so maybe that's like LeBron James, then his wingspan or his arm span might be 204 centimeters. So this would be a good guess that's what all of these things would mean. And then maybe down here you'd have a small child or something who had a foot of 5.38 centimeters, and you would expect their arm span to be 842. Sorry, I read that wrong. You would expect their arm span to be 38 point, I moved it, but anyway, around 38 centimeters. So that's how you would use a line of best fit. And we are going to use that in your work. So you're going to have a lesson tomorrow or next time you meet with a group. And with a group, you're going to be expected to do all of these things. So yes, you watch the video one time through. You might need to rewatch it when you're doing this again for yourself. With your group. And then keep in mind, eventually you're going to be able to use that data if you so choose to use this data to make some comparisons of your own. Okay. And I will give you some data I will give you 81 random people from the United States if you want to compare one-to-one that way. You can also pick other data that you find more interesting, right? You're a soccer player and you want to compare US soccer stats to Europe soccer stats or something like that. You are more than welcome to take other things and be more creative in a couple of days when we make this decision. Okay, that was I know there's really long. I hope you learned a lot. There's a lot in there. Great job.